So our last problem in our acid-base section here really is kind of an application of acid-base chemistry. Very common to use titrations to what we call standardized solutions. So we want to standardize a hydrochloric acid solution, and we use a sodium hydroxide solution that's of a concentration that's known to a high degree of accuracy. So this is the idea of standardization, and you have something that is an unknown concentration and something that's a concentration that you know with a high degree of accuracy. And so we'll see titrations with acid-base chemistry a lot. You can do redox titrations. You can actually do precipitation titrations, all kinds of ways to use a known concentration of one species and a balanced chemical equation to find the concentration and thus amount of another species. So let's just kind of walk through this problem, and I like to draw pictures a lot of times because maybe I don't quite understand what's going on, so a picture always helps. So we want to standardize an HCl solution, and I should note that there's another zero that's here. It's 50.00 milliliters of solution. So we're going to put that in a flask. So I'm going to have a flask over here that has my 50.00 milliliters of HCl. So here's my flask with my solution in there. And then I have a burette. So if you haven't yet started doing titrations in lab, you might not know what a burette looks like, but a burette is essentially like a very tall, skinny cylinder where you can measure volumes very accurately. And so I'm going to have 1524 molar sodium hydroxide in this solution. And they tell us that the volume initially is 0.55 milliliters. And then after we're done with our titration, and we can tell that we're done with our titration because this solution is going to become colored because of another chemical that we put in there. So as soon as all of the HCl is gone, it's going to change the solution's color. And so that's how we can tell that we're done. And so we see that color at 33.87 milliliters. So if we want to find the total amount of hydroxide, sodium hydroxide that we added, volume final minus volume initial will tell us that we've added 33.32 milliliters of sodium hydroxide. Okay, so why are we mixing these two together? Well, they perform chemistry. So HCl is going to react with sodium hydroxide and generate water and sodium chloride. And again, I'm not going to review why that is. If you need to, go back and review sample problems 4.6 and 4.7 to think about how acid-base reactions happen. Again, double displacement or swapping partners. But here's what's going on here. All of a sudden, this just becomes a stoichiometry problem like we've done in Chapter 3. We know that we have 33.32 milliliters of this sodium hydroxide, and we know that the concentration is 0.1524 molar. Because we know the molarity, we can convert a volume into moles. So now we know moles of sodium hydroxide. We can use, in this case, our balanced chemical equation. Stoichiometry was 1-to-1, so we didn't have to worry about any coefficients. We can balance this and know that we can get from moles of sodium hydroxide to moles of HCl. And we know for HCl that we have 50.00 milliliters of it, and the problem is asking us to determine the molarity. Well, remember, molarity is the moles of solute, in this case HCl, in the total liters or the volume of solution. Well, they told us the volume of solution that we had, and through this small unit conversion walk, we can figure out the moles of HCl. So once we figure out the moles of HCl that we have, we can divide it by the volume that it's contained in, and we can get the molarity of our starting solution. So I know I went through that pretty quickly, but again, I'm assuming that we're pretty good at our Chapter 3 material, so that stoichiometry problems are pretty straightforward. So let's go ahead and set that up. Again, I'm going to take some liberties here and automatically convert this mentally into liters. So 0.03332 liters of sodium hydroxide. I can walk between the volume and the number of moles using the molarity. Again, this is my molarity. And then I can change who I'm talking about by using my balanced chemical equation. And from this, I get that I have 5.0780 times 10 to the minus third moles of HCl. To figure out molarity, if I know how many moles of HCl I have, I just calculated it, and I know the liters of solution that it's contained in, well, they tell me that in milliliters, I can figure out molarity. So again, molarity is going to be the 5.0780 times 10 to the minus third moles of HCl. I'm going to convert this 50 milliliters into liters, 0.05000, 4 significant digits there. Liters, which means I'm going to have 4 significant digits in my answer, 0.1016 molar HCl. Okay, and just a couple of hints here to kind of help you with things. The stoichiometry here is 1 to 1 to 1 to 1. The volumes that we have are not that far off from one another, okay? So the concentrations shouldn't be wildly different. See if this makes sense to you guys. I have less solution in sodium hydroxide that I need to equal the total number of moles here because my concentration is greater, okay? Higher concentration solution means we need less of it to completely react with a larger volume of a smaller concentration. Okay, just a little heads up here. Do not be tempted to try to solve these problems with this equation. M1V1 equals M2V2. Do not use this with these problems. You will get yourself into trouble if you start using a dilution equation when you're doing stoichiometry. Okay? The only time this will work is if you have 1-to-1 stoichiometry, and I promise you that will not always be the case with acids and bases. So you will get yourself into trouble if you start trying to use that equation. Just a little side note, because I know sometimes students will try to use it. They'll get the right answer when they use a problem like this, but then you will get horribly wrong answers with many other problems. Okay? So follow this methodology that we've worked out here, and you will always get the right answer for a titration problem.